So in today's lecture, we're going to take a look at and use Gauss's law for a bunch of different situations. This first one is a new situation where we actually have to use a cylinder. Two collinear conducting cylinders are shown. The outer cylinder is charged to positive Q. This is outer black one here. And the inner one is charged to negative Q. Coaxial cables are actually used quite a bit in terms of audio and radio frequency signals, quite a bit. Oops, I've got the charges backwards. Sorry, the other one should be negative Q. The inside one should be positive Q. Let me fix that real quick. And the question is what is the electric field inside, outside, and in between these two things? So let's take a look at it. We're going to define the length of this as L. Even if they don't define the length inside of the actual experiment, usually just define L. L will cancel out. And so to find the electric field, let's talk about this a little bit. I can't remember if I put it in there. So we're going to draw a Gaussian surface in between the two. I'm actually going to answer this one first. So in between here, how much charge is enclosed by this cylinder? And before we do that, I probably should talk about the electric field lines. What do the electric field lines doing? Well, they're pointing straight outward from the inner one to the outer one. Remember, the inner one's positive, the outer one's negative, and these will go out in all directions. I'm going to draw them on the end cap here just to make it a little bit easier to see. But all the way around like this. And so in our Gaussian surface, we're safe because at every single point, it'll be perpendicular to that. I'm going to erase this one here and put it back there. And so we can solve this fairly nicely. And again, remember, this is actually happening at all points along here. So solving that, using Gauss's law, in this case, the field is only going through the outside skin of that cylinder, not through the end caps, because remember, this is part of a very long piece. So the field is just going through this outside skin of this little piece right here. So the area of that is just 2 pi r, the circumference of this, times L, the length of it. There is no field going through these two end caps, these pieces right here, if you can think about it that way. All right, so solving that, what's the field in between? And the answer is that. Now, what about the other questions, or the other ones? For r less than a, forgive me as I try to draw this inside of here now. For r less than a, we put another cylinder inside of this one, which has a radius that's less than a. And how much charge would be inside of this? The answer is none. And so very quickly you can infer that the electric field there would be 0. And then finally, what about the outside? Well, the outside, if you drew a Gaussian surface, which would be a cylinder surrounding these cylinders, I'm sorry it's getting so messy, how much charge is enclosed inside? The answer is, again, 0. We have as much positive charge as we have negative charge. And so you end up with no net charge enclosed inside. And so again, the electric field outside is 0. So it's kind of an interesting graph if you made it real quick. If you graphed electric field versus distance, I'll call it R. Here's point A, here's point B. Before that, we have no electric field on the inside, and then suddenly it's going to jump up at point A, and then decrease as a 1 over R curve to B, and then drop back to 0. All right, moving on. These next couple slides are a bunch of AP questions. In the figure above, a non-conducting, now pay attention to that one, solid sphere of radius r, which is charged with positively Q, uniformly distributed throughout. If you have a conductor, the charge immediately goes to the surface. With a non-conductor, you can distribute charge throughout it. So think about this like a charged plastic sphere. And now the question is, what is the field for each one of these? And I don't think did I put answers on here? No, I didn't. Sorry. So let me quick do a couple of these. So if you're on the inside, how do you solve this? So imagine R is inside of this thing. How do we figure out how much charge is inside of this Gaussian surface? Well, you might kind of quickly figure out that it's going to be a ratio of the volumes. The volume of that's within my Gaussian surface, 4/3 pi r cubed, over the entire volume of that, which is 4/3 pi a cubed. All times q, and that's going to be my charge inside of my Gaussian surface. So solving point 1 on this one, I'm going to jump right away to the end here. Electric field times the surface area of my Gaussian surface, 4 pi r squared, is equal to the charge inside, which is given by that rather large expression. I'm going to write it backwards over here, up above. Can I be lazy? I'm just going to write r cubed over a cubed. I don't know if you can see the cubes up here. That's actually kind of bad. All over epsilon naught. And if we solve this, we get rid of a few things, but the electric field on the inside, this is for point 1, is just going to be given by the total charge, or charge Q times R. That's a really bad R. Over 4a cubed epsilon naught. Make sure I did my math right. A cubed mouse down there. 4 comes down there. Yep, that should be right. For part 2, between. So when we're in between here, the total charge inside my Gaussian surface will just be Q. This becomes much simpler. This will be just electric field. Oh, I should draw my Gaussian surface, sorry. Here is going to look like this. R is now coming out all the way to here. We're going to end up with electric field times 4 pi r squared is equal to the charge inside, which in this case is just Q, over epsilon naught. And so in this case, for part 2, pretty simple between the two. Electric field is just going to be equal to Q over 4 pi epsilon naught r squared. Now finally, within the spherical shell, somewhere between there and there, this one is not as easy as you would think. Why? Yeah, it encloses all of the positive Q, but it also encloses a fraction of the negative Q. So what you have to solve on this one is how much charge. Oh, let me do the easy one first. What would be the electric field outside of this thing? Well, if you make a Gaussian surface outside, the total charge enclosed inside and outside is 0, and so the electric field ends up being 0. But for part 3, this gets a little bit interesting. I need to figure out how much negative charge is in this region right here that's going to offset some of the positive charge that I have on the inside. Please forgive me for my really bad scribble. And so solving this one, it's going to look something like this. We can go ahead and do the easy part first. E times the area of my Gaussian surface, 4 pi r squared. And now here's where it gets a little more painful. What's the charge inside? And forgive me in advance for how painful this is going to look. Well, it's all a positive Q, but minus the negative charge. So in this case, we've got a certain fraction of that negative Q in here, but we have to, it's going to be this volume over the entire volume of that. And this is where the painful part comes in. And I may not have left myself enough room here, but I'll try to write small. It'll be 4/3. You know what? I'm going to make this a little larger, just so you can sort of see it better. And erase that and that. I'll put it in after I finish. It'll be 4/3 pi r cubed, which would be a volume of a sphere all the way out to this point, minus this empty space inside here. So minus 4/3 pi times 2a cubed. So that'll give me the volume of that green shaded area there. What's the entire volume? Well, we got to do the same kind of thing again. It'll be 4/3 pi, the outer radius of the outer one, which is 3a cubed, minus the inner volume. And at this point you might say, oh good, the 2a cubed, or the 2a cubed is going to cancel out. And my apologies, I need to fix that up top here. That cube is outside. But no, rules of algebra, you can't quite cheat that way. And that all thing is over epsilon naught. Which is why you can sort of see why I was cringing about this. So that whole is the fraction of negative q we have inside of this. Doing a little bit of algebra, let's see. Can't do much with this one. Let's see, we end up with 8a cubed up on top. I guess we could remove all of the... Yeah, there's not much we can do with this one. What's the electric field then in between here? It's going to be equal to, and I'll factor out the Q times 1 minus r cubed minus 8a cubed. That's numerator. And then the bottom denominator, we have 3 cubed, which would be 27 minus 8, which would be 19a cubed. So that whole expression over the denominator, which is going to be 4 pi epsilon naught r squared. And that is a rather hideous expression for number 3 within the spherical shell. Yeah, that one's horrible. So that's 3. All right, that was horrible, but it's actually a real AP question designed to take 15 minutes. This one, I only want you to do A and B2. We have not talked about equipotential lines. Use Gauss's law to derive an expression for the magnitude of the electric field outside the rod. So in this case, we've got a non-conducting rod. It has charge distributed for its volume, but instead of giving us rho, they gave us lambda, which is the charge per unit length of this rod. It's all right, it's fine. Solving this one, we're going to define the length of my Gaussian my cylinder as L. So plugging it in, again, the flux or field is only going through the outside skin of that, so 2 pi r times L. The charge inside is going to be sigma times the length, if that makes sense. Notice that the L cancels out, even though we defined it ourselves, and voila, we get the electric field. For B2, what are the field lines going to look like outside this thing? They should be pointing outward in all directions. Number 3. This one, you'll notice, has an asterisk by it. It was given about 15 years ago, and literally students cried during the exam. Why? Because the charge density is not uniform. It varies with distance. I'm not going to assume that you can actually integrate this one at this point. I'll do it a little bit later. But the question on this one is, we're told that a total charge of Q is on in this distribution, and the question is, what is the electric field at point P? How will you solve that? Well, you put your Gaussian surface through P. I'm not going to draw it all the way around. And to find the electric field, did I put it in here? No, I didn't. It's actually pretty simple. For point P, this first one, E times the distance r, small r, E times 4 pi small r squared is going to equal the total charge inside my Gaussian surface, which is Q over epsilon naught. So the answer for this one, even though this problem was actually really painful, I haven't shown you the rest of it, is simply this: Q over 4 pi epsilon naught r squared. And hopefully you could recognize that right away and go, oh yeah, I got that. All right, moving on. That's an r, believe it or not, small lowercase, squared. Here's another one. If you want to, you could pause the video at this point and actually give this one a try. So a very long, solid, non-conducting sphere or cylinder of radius r has a positive charge of uniform volume density rho. A little bit more consistent, the charge is distributed throughout the volume. A section of cylinder far from the ends is shown in the diagram above. Let r represent the radial distance from the axis of the cylinder. Express all answers in terms of r, big R, rho, and fundamental constants. Using Gauss's law, derive an expression for the magnitude of the electric field inside. Draw an appropriate Gaussian surface. Oh, I don't have the other one. So this is actually for the outside. This is actually answering B. For B, Gaussian surface is on the outside. I've defined the length as L. And just plugging it in, area is going to become 2 pi RL. The charge inside will be the volume of that cylinder that's contained inside it, just the part that has a charge, which is going to be 2 pi r squared, the area of this edge, times the length L up to this point, if you can imagine it. And if you solve that, you'll discover that. Do I have the other one in here? Oh, I do, I think. For the inside part, we're going to just define R here, and our Gaussian surface is now inside of it. Very, very similar. We're going to define that length as L. Whoops. And this time, what's the charge inside? Well, first of all, the area that the field is going through is still the outside edge, so 2 pi r times L. That's dA. Equals the charge inside, which is going to be rho times the volume of that thing, which is going to be pi r squared. Oops, sorry. Pi r squared. I wrote pi squared. Times pi r squared times length, all over epsilon naught. And let's see, we got a pi and an r will cancel, L cancels, and so the electric field on the inside should just be rho r over 2 epsilon naught, if I did my math right. So inside, electric field actually increases as r increases. On the outside, decreases as r squared. Number 5. At this point, we've been doing Gauss's law all the time. I love it when AP does this. AP suddenly threw in a rod and said, find the electric field. And guess what? Because the Gaussian surface would sort of look like a hot dog around this thing, you actually can't use Gauss's law for this one. How do you figure it out? Well, you figure out dq, you figure out the electric field dE due to that one, and then you know that in the end the net electric field is just going to be pointing this way. So you just find dE sub x for each one of these and then integrate it. We actually did one, and this is very much like your extra credit, except this time you actually have numbers. You've got lambda. So if you figure out what ds is equal to in this case, let me draw my little arc here. Pretend that's straight. This arc length right here is ds wide, and this angle here would be theta. And I'm just going to set it up without actually doing it, and this little angle here would be d theta. You can figure out the charge. dq in this case would be equal to lambda times ds, the arc length. And in this case, we know the arc length is actually going to be equal to the radius times d theta. We can now plug that into our integral. We know the total electric field is just going to be the integral of dE sub x. And we can actually write this. It's going to be the integral of the electric field, which is going to be dq. I'm going to write that in right away. Lambda r times d theta, what we just wrote up above, all over the distance times 4 pi epsilon naught r squared. And then remember, this is, we want only the horizontal component, so times the cosine of theta. Limits of integration, 60 degrees, which is going to be pi over 3. So negative pi over 3 to positive pi over 3. Excuse me for my pi's being so bad. And you can move all the constants outside of that. In this case, 1r cancels. We've got a lambda. We've got a 4 pi epsilon naught times r. And then all we have left inside the integral is cosine theta d theta. And I didn't even write the limits on this one, but all you got to do is integrate that one, plug in your limits, again, negative pi over 3 to positive pi over 3, and you've got it. Just off the top of my head, let's see, sine of 60 root 3 over 2 minus a negative root 3 over 2 just gives us root 3. So the correct answer on this one should be root 3 lambda over 4 pi epsilon naught r. And you can actually plug in lambda and r and actually come up with a number in this case, which is kind of cool. Oh, I didn't do A. The total charge on the rod is just going to be the total arc length, which is going to be 2 pi over 3 times the radius 0.1, and that'll be the total length multiplied by lambda will give you the total charge. All right. Lastly, number 6 on this one. We've got a conducting spherical shell of outer radius A and or outer radius B is inside, and a larger conducting one is on the outside. Each shell carries a net charge of that, and the outer shell has a net charge of that. Now, a couple quick reminders. With a conducting shell, that charge is going to spread out on the outside. So this positive 2q is going to be in the outside, this metal. Why? Charge in a conductor is going to move as far away from each other as it can, which is always going to be on the outside of that container. So sort of like this. Oh, sorry, forgive me. I'll just pretend there's plus signs all the way around here. But we've also talked about the fact that the electric field inside of any conductor must be 0. Now you might say, wait a second, if I draw a Gaussian surface here for the middle of this conductor, I've got a net charge here. Well, most of you at this point will be confident saying, oh yeah. What's going to happen here is there's going to be a negative 2q induced on the inside of this surface. So that now if I draw a Gaussian surface inside this outer conductor, you'll end up with a net charge of 0. Electrons and the outer conductor will be attracted to the inside surface until the remaining ones feel no force, no field. But that changes things just a little bit on the outside. We know that the net charge on this whole thing had to be positive 3. Well, now we've got negative 2 here. What does that do? It means the charge now on the outside of this, and I'm not going to draw them all, must actually be now, and see if this makes sense to you, on the outside positive 5q. You're like, whoa, I thought you said the net charge was positive 3. Yeah, it still is. Inside charge negative 2, outside positive 5. And so overall the charge is positive 3. And now you can actually solve this just with Gauss's law. They probably want to know the field inside and outside and all around this. Nice thing is, the electric field for all points less than, if R is less than B, the field is just going to be 0 because there's no charge inside of any shape there. That is, within this thing, or even inside of this shell, all the way out to B, there's no charge. What happens when R is greater than B, but less than C? Well, now we've got a little interesting problem. Yeah, we do have a net charge of positive Q. Hopefully at this point, maybe you're confident enough for me to just write this at this point. It would be 2Q over 4 pi R squared epsilon naught. And I'm literally just using Gauss's law at this point and plugging and chugging. What happens when you go inside of C all the way out to D? Well, now you're inside of the other outer conductor, and of course the electric field is 0. And then finally, on the outside, if R is greater than D, what do we end up with? The total net charge inside now is a total of 5Q. So it's just going to be 5Q over 4 pi squared. Sorry, 4 pi R squared epsilon naught. That is a really bad pi. And so you've got this one. And then number 7, I'm going to skip for the time being. You've got a positive charge in the center, negative charge distributed throughout the outside of this one. So this one's a little weird. So the negative charge, an equal negative charge, is distributed throughout this volume. It's sort of like plum pudding model, if you remember Rutherford back from chemistry. Whereas all the positive charges on the inside, the negative charge is distributed all over the place. So what's the electric field on the outside? Let me do the easy one first. The electric field on the outside is going to be 0. Why? Out here, you've got an equal amount of positive and negative charge. Any Gaussian surface out here, the net charge inside would be 0. What about inside? Well, that gets a little bit more exciting. So for inside, we have to figure out what fraction of that negative charge is inside of that. And here's where it gets a little more exciting. So it's going to be E times 4 pi, the area, R squared, equals the charge inside, which is going to be all the positive Q, plus the negative. I'm just going to, instead of saying plus negative, I'm just going to say minus Q. And again, we're going to do that same ratio thing we did before. 4/3 pi R cubed over 4/3 pi big R cubed. Yeesh. Sorry for my handwriting. All over epsilon naught. Solving this one, 4 pi, or 4/3 pi on both those cancel. And I can reduce the R slightly. we end up with the electric field just being Q times the quantity 1 minus, let's see, what can I do? I can't do much with this one, sorry. R cubed over R cubed. All over 4 pi epsilon naught R squared. And I was trying to figure out if I can reduce that. I can't see it. Finally, let me go through the details now on this one, just so you can sort of see it. Warning, I realize this is probably the most difficult question they ever asked. This is 1992, ENM 1, and the charge density, rho, is not constant. And because it was the first ENM problem, and I told you this made people cry, they literally gave up on the whole ENM section. It was the lowest scoring year in a long, long time. So rho increases, that is the charge per unit volume, increases as some constant times the radius. And so if we take a look at this one, first of all, I want to do part A here. Show that the total charge in the spherical region is given by beta pi a to the fourth. So doing that part, I'm going to first solve this part here. So because each different radii has a different rho, I'm going to break into a lot of little thin little shells, almost like an onion, and then add up the charge on each one of these little onion pieces. The total charge then is going to be rho times the volume of this little tiny piece that I've got drawn here. Well, the volume of that little piece you can either get by calculus or realize that, wait a second, it's basically just the surface area of this inner sphere times the thickness. In other words, dV is going to be 2 pi r squared. That's the surface area times dr. For those of you in calculus already, yeah, you could also do this, since you know the volume is equal to 4/3 pi r to the third. Yeah, you could simply take the derivative of this with respect to r, and you would get this expression down here. Sorry, let me take that out now because it looks confusing. You're like, wait, dV dr is equal to that? No, that's just the volume. Plugging that in, we can now solve this. We just have to integrate from the center all the way to the outside of rho times dV. In this case, dV is given by that expression. And if we solve this all the way through, we get this. Substituting in BR for rho, which is up here, we'd get that. Multiplying around there, we get that. Moving the constants outside, we end up with that. The integral of r to the third, of course, is r to the fourth over 4. Plugging in our limits, you can probably see it real quick. The 0 is going to cancel out, and you simply end up with that. So pi beta a to the fourth. I didn't quite have it in the same order, but you get the idea. We can then use that to solve this other part. So what is the field on the outside? Well, that's pretty simple then. What's the charge inside my Gaussian surface? Well, pi beta a to the fourth, number we just got, all over epsilon naught. And solving it then, we get that. And then what about when it's exactly equal? Pretty straightforward. In that case, a's actually kind of cancel, and you just get that. In this case, the radius of my Gaussian surface is the same as the radius of this thing, and so a's cancel. It's nice. And then finally, on the outside, same kind of thing. The total charge inside of my Gaussian surface, whoops. Oh, wait, this is inside. I'm sorry. Is going to be this r here, not a, because we're not dealing with the whole thing. It's just the charge in this region, which we know in general is given by this expression. And in that case, we get that. That is probably the worst one that you can have. There's a couple other sample problems, I think, in your notes. We'll talk more about this. This one you've actually seen before in your notes. But hopefully all this kind of helps you with the homework tonight. Good luck. Good job. Hang in there.